Cool. We've kind of divided this into like two major sections, and the largest being under constrained circuits. We don't have any over constrained circuit examples, so if you guys have those, please, we're really dying to see one of those. The idea being that you could have a valid input go into an honest prover that would fail the verifier, right? Or a valid input that would fail the prover and never get past that first stage. But anyways, we've kind of split some of these up, so we're going to be like tag teaming the different examples and stuff, but we'll walk through them. I'm going to hand it off to Jens to talk about just like the general under constrained case.
Cool. So yeah, let me talk about missing constraints in general. So essentially, this is like a bug that directly translates from Merkle tree implementations as you see it like somewhere else, for example, for certificate transparency. And what this essentially does is like it enables a second pre-image attack. So just if anyone doesn't know, like you have like a simple pre-image attack where you have a hash. Usually hashes are collision resistant. So you have like one pre-image, one hash, right? Second pre-image in this case is essentially you find like not like the same pre-image, right? But like a second one, right? And in Merkle trees, this is particularly interesting because you have like different layers of hashes, right? So you have like on the bottom, you have like the data blocks, and then you have like intermediary hashes and like the top hash, which is like the Merkle root. So essentially, to get to the Merkle root, you don't necessarily need to hash like the data blocks, but it's like if you have like the intermediary level, it's like sufficient to hash like the in-between ones, right? And this is a common bug that is like fixed in standard implementations of Merkle trees as well. A simple fix in order to fix this would be distinguishing between leaf nodes and branch nodes, where leaf nodes are like the bottom ones and branch nodes are like, for example, the intermediary ones, by prepending like different byte values. Or you kind of like in the implementation of the Merkle tree, you record the tree depth or the node depth, right? So yeah, could you forward one? Thanks. So that was like an issue in the Plonky 2 implementation of Merkle trees. So they actually didn't distinguish between either leaf nodes or branch nodes, and they also didn't check for the shape of the public inputs. So yeah, so what they're trying to do now is like kind of like records the tree depth as a fix. And that is kind of like merged into the implementation, but this shows that kind of the bugs that are known in common implementations of Merkle trees and other primitives directly translates to implementations in circuits as well, right?
Awesome. This is, and a lot of these are actually going to be overlapping different categories, but this one it'll keep coming up throughout the presentation, so just want to like talk about why. The arithmetic under and overflow. So there's this large prime field, and basically all the math that happens, all the multiplication and addition, ends up getting multiplied by mod p. And so you can have the same kind of like traditional security bug where we see integer overflows, underflows. We have like a similar type of thing here, except there's no, sometimes we want it. If we're generating randomness, it's okay for it to overflow, but a lot of times we don't. So the idea being here that like there's P is this like large prime, like the order of the set of primes, right? And this is a much smaller one, this example right here, just so it fits on the page. But if you subtract 1 from 0, you end up with P minus 1. And if you add 1 to basically P minus 1, you end up with 0. And your circuit's not going to tell you this, right? So a lot of times people will do like addition or multiplication, and they're reasoning in like 256-bit, numbers in their mind, but the field can't actually support that. So you end up with cases where you have non-determinism. You have potentially the ability to make like two nullifiers for a given deposit, like in privacy pools, things like that end up in double spins. It's really bad. Just a side note, for ZK EVMs and most of it's like Halo 2 implementations and CIRCOM as well, everything that like has to basically be verified in Solidity potentially. The order of the curve is the order of the curve for BN254, which is the only pairing-friendly curve supported by the EVM. And that number down at the bottom of the screen that I'm not going to even try to repeat is what P is in this case. And it's kind of crazy to think that like you might actually ever be reasoning about numbers this large, but if you're dealing with like GUI and gas, or if you're just subtracting something from 0 or from a low number, it's very easy to end up in this realm. This is a great example, and thank you to Edward and CC and the rest of the PSC ZK-EVM team. A lot of these examples are from them. The bug tracker that we do have with 0xPark had a lot of SIRCOM examples, and since Halo 2 is so new, it was hard to find these examples, so they were great in providing a lot of examples here. So this is a bug where there's a very specific case in the SAR opcode that made it vulnerable to overflow. And it also ends up meaning that we kind of like need a spec change for ZK EVMs, because the way to fix this is actually to constrain this shift divisor 64 to being under 4. And I could walk through all of this, but since we lost 30 minutes due to technical difficulties at the beginning, I think we'll just kind of skip over this. But if you guys are interested, glad to talk about it later. The fix is right here. These 2 lines added to the top, you can see. Basically, this shift div 64 is less than 4. That constraint is required here. Otherwise, the lower constraint, you can see the green part with the double equals. This actually is vulnerable to overflow, right? That multiply by 64. And the actual like logic and reasoning about this, you can see down at this GitHub link, there's an issue filed here where it talks about like how to come up with the attacking case and how to reason about it in terms of like the order of the set. This is another interesting one, this Aztec tree index bug. This is another area where there was like a Merkle tree index issue. This is slightly different. There's actually been 3 or 4 different bugs related to Merkle trees. Most of them have been about like where you index. This particular one is like a typing issue as well. So we're going to talk about like typing and bitlink bugs as well. This is also in that category. The idea being that Aztec has a privacy pool that's similar to Tornado Cache. So you end up in this like, you store all the data in a Merkle tree, but you end up with this like idea where you have a pre-image that's secret, and then you have like 2 hashing functions. And whenever you submit the ZKP to withdrawal, you're proving that you have the pre-image of a deposit that has the same pre-image but with a different hash. And so you end up with this idea of like a nullifier. So when you're withdrawing, you're proving that you have this pre-image, you have a note that did one of the deposits, but not proving which one it is necessarily. And whenever you do the withdrawal, you create a nullifier, and this prevents you from being able to withdraw the same funds twice, which would be a double spend. In this particular case, the index into this tree had a max upper bounds in code of 32 bits. But the problem was that the circuit itself had an input that was the entire prime field of the set order P. And so it's possible there's actually 2 different inputs, one of them being like the index mod P and the index plus P mod P. And so like the way to kind of think about this conceptually is like if I have, actually I want to write this up here really quick. And I hope that, let's see, it'll be on this side. Because this is such a common bug, I think this is maybe one of the most common bugs that we see is related to this overflow. Like if I have like 9 mod 5, right, that equals 4. If I have 9 plus 5 mod 5, that also equals 4. So if we're doing something like checking, and in this case, 5 is P, but P is like really freaking big in these circuits. It's too big to like reason about, like, but this is the idea behind it. So if you are providing the index into a tree as one of your constraints, there's actually 2 indexes into the tree after you mod P it that will both give you the same index. But if you're hashing that initial index, you're hashing 9 and you're hashing 14. And you're going to get 2 different nullifiers. Like if you're using the hash for a nullifier, you'll end up with 2 different nullifiers. So every deposit can withdraw twice, that like 2 times, right, and still pass all the constraint checks. And this is like super common in these privacy pools. It's also like an issue for other reasons that we'll run into in a little bit. This is another one that's kind of overlapping. We talked about like types and like links. So strong type checking is something that like permeates like traditional security research. We see like type bugs all the time in memory unsafe languages, but we also see like security tools, linters, and like compiler like warnings that help us like reason about typing stuff. And this might have helped here. And we'd like to kind of discuss and get feedback from you guys in the end in the like brainstorming session, how we might go about applying like these traditional security research methodologies towards circuits so we can prevent these types of bugs. So PSE had this less than chip, and the way it basically worked was that it if you give it like 8 bytes, it will go through the greatest byte, right? And it will do like a less than on it and basically compare them. And if those were compared okay, if they were equal, then it would iterate down the like section. So at each stage of this circuit, for optimization reasons, it's only reasoning about 8 bits, right? Just one of the bytes, right? And so the problem here is that there actually wasn't this particular diff variable wasn't actually constrained to be like just that particular byte. So it's kind of hard to like think about this, but like the developers thinking about the optimization here being that, you know, we only have to do the circuit stuff to reduce the number of gates. We only reason about each byte. We walk down. It's like this optimized structure. But the person that's using the less than chip here, they don't actually like totally consider this, right? And so the way you can reason about this chip that it's different is that if I'm doing less than on 2 8-byte numbers and I'm comparing them, I'm actually providing 8 inputs for each to the circuit. So it's kind of like a tricky, like under the hood, it's using the whole prime field. It's not using these bytes that you're thinking you're giving it, right? And let's see, I'll kind of skip through some of this. Yeah. Here's another one where there's a cast though. So like the way that you can reason about this, right, there's this shill opcode. It takes in shift 0 as an input, which is supposed to be the first byte of the shift input. It was assigned correctly, however, it was not constrained to a single byte. So this first line, it says pop, and it basically is a casting, right? So this is like a very common thing where we have an equals or a double equals in CIRCOM. We have an assignment versus an actual constraint, right? And in CIRCOM, you can do both at the same time. You don't do both at the same time in Halo 2. So it makes it where we kind of have like 2 sections, and we can maybe reason about them and like diff them, and that's kind of somewhere where we might have a strategy moving forward that we can discuss. But in this particular case, this shift 0 is basically like casted to a byte here. But when the constraint is made, it's not, right? So this particular constraint is trying to basically say that like the divisor high is constrained to 2 to the 128th minus the shift, right? And that fails here because up here where shift 0 is, we get a cast, but the actual input to this constraint is not like casted per se. And there's no way to like cast in these constraints that we add unless we add a bounds constraint. That would be like the effective like cast that you could think of in like traditional software, right? So the fix here, it's basically saying, make sure that shift 0 is equal to that cell. So like don't actually just cast shift 0 to just be the first byte, like consider it the first byte. After you do it, check that it's equal to the whole entire input, right? Because if that's the case, then you know that those are all zeros on the other bytes, right? Assign but not constrain. This top example is the one that we just talked about, where there's like an assignment, but there's not actually like a constraint. So I won't go through that. I do want to talk about this MIMC hash one real quick. MIMC hash is used in Tornado Cache and other things. It's just a ZK-friendly hashing algorithm. So during a computation step for the circuit, there was this equals operator instead of this like arrow doubles equals. And this is CIRCOM, right? And a lot of these examples are in CIRCOM and the bug tracker. So if you're not a CIRCOM dev, you can check this out and they're relatively easy to understand. It helped me like reason about the Halo 2 examples that these other ones that we have, just going through those. So basically what ends up happening is that you effectively assign out 0, but did not constrain it, allowing an attacker to have some leeway to change the MC hash. So this doesn't make like a double spin like just completely easy, but it makes the like brute forceable like set that the attacker has control of a lot wider. So what they can do is they could potentially bypass and provide a hash, or provide like basically use a pre-image to a hash that's not the actual one to do the withdrawal, because it's more likely they can find a situation where there is like a 2 pre-images, right? So like the non-deterministic case, and we'll talk about more of those in just a second. Also, if anybody has, I'm moving fast because we lost 30 minutes, raise your hand and interrupt me if you have questions or if you have a really good idea or something like that. Non-deterministic circuits. This is just like that last one. Like a lot of these overlap, like I said. Basically, like there's more than one way to create a valid proof for a certain outcome. So in the case of the modulus, this is an example. 9 and 9 plus 5, right, 14, both would, if the constraint was to make sure that the input mod p, which is 5 in this case, is 4, these would both be valid, and they would both pass that constraint. So it's non-deterministic is the way we think about it. And it's a little bit backwards. When I think of non-deterministic, I think there's like two outputs, but like it's in the circuitry, there's no like in and out. It's just a system of like nonlinear equations that kind of like have to equal, right? That have to be satisfied. Double spin examples have all been this. It's been nullifier issues. We talked about the MIMC hash one. We talked about the Aztec tree index one. There's another example where there's a Peterson hash input. The way the Peterson hash works, you basically have like 128 2-bit windows whose sum is equal to the input, right? And what ends up happening is you have two possible representations in this 2-bit window that you can make to have the same like sum. So there's basically like two possible inputs that are calculatable for every output, right? So you could have a double spin pretty easily this way as well. Compiler optimizations. There's two compiler optimizations that we've identified, and there may be more, and I would love to hear if you guys like have examples of this too. These are like, the way I reason about them is like, they're no mistake of the developers. But like if you guys are using, I have a CIRCOM example and a Halo 2 example. If you guys are using these proving systems, like you need to be aware of these when you write circuits, because what your circuit is doing is not what you think it's doing, basically. This example I actually took from the ZK IAP. If you guys search like ZK IAP 0xPARC, in Boston they recorded all these lectures at MIT for like a month-long study session that happened in January. It's a killer class. A lot of you guys are actually teachers in it. Thank you guys so much. It helped a lot. This particular example, I think Vivek had in the CIRCOM 2 like workshop. And basically the idea here is that we have like a very simple like public-private key signing algorithm. And don't think like RSA, ECDSA. Think like a zero-knowledge version of that relies on a circuit under the hood. Basically, we have an input, an M. We have a secret key and a private key, right? The secret key being a private, like a witness to the circuit that's not public, right? And there's this hashing algorithm. Basically, it's just the Poseidon hash. So you take the secret key. You basically are proving that, like, given a public key input, you have the preimage to the Poseidon hash that equals that, right? So what ends up happening here is that you think if you're calling this, you have two public inputs, the message and the public key. The developer is reasoning about this as like, hey, if I give the public key and the message, and that's a public input, everybody can verify that, and I have the private key as the witness, I can generate a proof that they can verify against that shows that I'm signing a message here, and I'm signing this message. But there's a problem here. Message does not have any nonlinear constraints. So what ends up happening is the same, like message is just optimized out by a CIRCOM compiler. So if I sign a message with my private key, basically, I admit a proof, an attacker can take that exact same proof and replay it with a different message, and it doesn't matter. It's still going to pass the verifier here. Right? So this is like something you think, the way you reason about it is like, hey, I've got two public inputs, one private input. That public input is just floating, right? It's non-constrained. And so this is like a pretty big deal. You can see why like this looks like it makes sense. If you were to like draw this out on the board, like with a box, two inputs and one private, like two publics and one private, you'd think you're doing what you are, and you're not. The way to fix this is really funny. You just add a dummy signal. You make a nonlinear constraint for M squared. M squared doesn't have to be an output or anything. It just, if you do this, it adds entropy to the proving system. And then if you change the public input, the proof will look different every time. And that prevents this replay attack issue, right? This is not common in the same way as a mistake in Halo 2, but it is very possible to do still. Question?
Yeah, but you're not constraining that M is signed by the key there also. So you could create a proof with a message that is signed by someone else.
Yeah, you probably should hash. You're right. We should probably like hash the public key against this.
Yeah, you should bet constraint. So I don't think the product is a compiler optimization. It's like it's under constraint. So
Yeah.
it's like a under constraint.
But I think the proof is the signature.
Yeah, the proof is the signature. So the proof would look different with a different message.
Okay. Oh yeah, because you have the private key. So okay, yeah.
I agree though. Like
Okay.
to conceptually,
Signature. Okay.
yeah. Like the proof would change if the public input changed. But it would make me feel better if the secret to public like was also used in this dummy variable or something. I don't know that it might not actually change anything, but like, I don't know. deep down, I have like a feeling that someone's going to figure some weakness out here anyways. That's more like related to the hashing function or something, right? Cool. In Halo, oh, I do want to mention this. In Halo 2, you don't make the same mistake because the compiler optimized it out. You make this same mistake because you don't reason about making sure there's, you have to forcefully add a nonlinear constraint to any public inputs in Halo 2. Like, so it's almost like the dumb thing that the compiler did here, you still have to reason about it in this way as a circuit developer to know that you need to do something with M that binds it to the proof that's output, right? Cool. This one's an interesting one for Halo 2, and maybe Edward and Yingtong, if I botch this one, jump in and correct me. Basically, it's common for advice columns to be used as lookup tables. So like there's certain operations that are really expensive. If the input space is small enough, you can just pre-compute them and make a lookup table. So like you can think like, if I'm only gonna like SHA-256 the opcodes for the EVM, and there's like 120 something of them, then like I might as well just do all of them ahead of time and not make circuits that are like adding like, you know, minutes to our proving time to do these things. I could just make a lookup table, right? The idea there though is that you have like a static lookup table. You pre-compute them and you stick them in as like constants. There are such things as dynamic lookup tables. So like the assignment of the like the key, the value in the lookup table for a given key is actually like based off of like some multiplication or addition from some other cell. When that happens, sometimes you leave rows empty, and the floor planner that moves all the different regions in Halo 2 around to make like the most optimized circuit will just overwrite them or leave them completely unconstrained. So am I getting that right? Cool, all right. This was actually like a new type of bug class that we like sort of discovered maybe 2 days ago and added in here. So there's potentially some fixes here, and I think Yingtong has like a PR out right now for Halo 2 to make it where you can tag a column. So the idea here being that like if you leave rows empty, they end up unconstrained, or there's like garbage there. If you tag a column, then every row that like is an ancestor of that column can basically, you can tell the compiler like, hey, preserve everything that I'm assuming about this region. Don't put anything else here. Don't leave it unconstrained. There might be other ways that we can do this. There might be other, I think Snarky may be vulnerable to this. I don't know enough about it. But anybody that has dynamic advice lookup tables that also has some sort of like pass-through step like the floor planner that does like an optimization of the circuit like architecture this is like an assumption where the compiler could like basically screw the developer here, right? And the way the developer's reasoning about the circuit. Cool, I'm gonna pass the frozen heart vulnerability over to Mohammed.
Hello everyone. So this one is very old by now, but essentially Frozen Heart is the name that Trail of Bits people came up for this class of bugs that is related to misuse of fiat-shamir. So whenever we have an interactive protocol and we want to make it non-interactive, we use fiat-shamir. Basically, you need a randomness from the verifier, hash the transcript. That's the idea, but the problem is, or the tricky part is, the transcript has to include everything, and you can't omit anything. Like, the statement must be in a part of the transcript. The previous, random challenges must be in transcript. And if you, somehow forget to include some of these things, it may enable a malicious prover to forge proofs for random statements. Like, it don't enable you to prove any statement you want to, but you could come up with statements that are provable for you, something like that. It can be severe depending on the context, and the way to fix it is to, whenever you're using fiat-shamir, make sure you're adding everything that's in the transcript to the transcript. So there is a simple example for it. So if you think about Schnorr signature verification, the non-interactive version, I wrote it down here. So you have a private key, it's X. You have a public key, it's Y, which is equal G to the power X. So you hit the private key in the exponent. And now you want to prove the knowledge of X without revealing X. The way it works is, specified here. It doesn't matter. The detail is not important. The purple line is where we use fiat-shamir to eliminate the need for interaction. So the prover generates randomly this random challenge C hashing the transcript so far. But the question is, what is the transcript? If we just put B, the previous message, as the transcript, which was the common practice like almost a year ago in many of the libraries, we are in trouble because we are omitting the statement. What is the statement here? The statement is probably, the public key, right? And it binds us, if we, include public key in this hash, it somehow binds us to the public key that we committed to. But if we don't do that, we get to do things in the wrong order. And what does that mean? We find a public key, we first find the proof and then find the public key that, works with that proof. The way it works is, if you look at the algorithm, you need to, as a prover, you need to give a random value B. You just select an arbitrary value, you calculate the challenge, and then you need to send a Z that has a certain structure. But instead of that, you pick a random Z and find a public key that satisfies that structure. And it's actually very efficient. And at the end, you get the proof Z for, it's a fake proof because it's proving knowledge of the discrete log of PK, but we don't know this discrete log of PK. So something like that. And yeah, I mean, if you're developing a proof system, you should think about this. But also, if you're using, if you're making an interactive protocol non-interactive in your, application, maybe it's not a proof system. You should be wary of that.
And the way I reason about this is like there's like this commitment part, but there's also the number of iterations of the Fiat Shamir. So if you're making something non-interactive, not only do you have to worry about what you're committing to, if you're, you only iterate 5 times, that's much easier to find a collision, like potentially like a proof that could pass a verifier, even if you don't actually have like a valid witness. It's much easier to do that than if you iterated this Fiat Shamir like 150 times. Like you can think about the way that every time we update Wi-Fi with the new spec, we make like a harder, like a computationally harder hashing algorithm for the handshake. That's the way I think about it. All right, this part is where we're gonna like kind of open this up for like questions, for like different suggestions. We wanna hear back from you guys. We have like, we kind of went through like a bunch of the common vulnerability like classes, and then we have like maybe some ideas, like roundabout areas of how we can attack these things. So we're gonna go through these like kind of like briefly what they mean and describe them. And then I think the rest of the time is literally gonna be like bouncing around between like, wait, let's reason about this example, and then like knowing what we know about like potentially fuzzing or formal verification, can we apply that here? So given that, I'll give it to Tyler to talk a little bit about fuzzing.
All right, so fuzzing basically is an automated testing methodology where you start off with a corpus of unique inputs for a test case, and you define some way to mutate that corpus to find more interesting tests. So why it's desirable here is it allows you to, with very low input of work to define this initial test case, it allows you to generate a bunch of new test cases and continually test your software. Right? You don't have to constantly be going through and writing new unit tests. This is something that automatically gets done in the back. And why this is nice for ZK EVMs is because there's a lot of fuzzing infrastructure already in place for the regular EVM implementations. I mean, this is something we're constantly doing. So we have a rich set of corpus that we can already pull from. And so what we're trying to get out of this is right now there's not a lot of public-facing projects for fuzzing ZK systems, so we want to change that. And we also want to generate really good corpora for fuzzers to use. So people can take corpora that we've generated or that we're using and build on it and give us their inputs. A good example of that would be, let's say we're doing differential fuzzing for the standard EVMs. We find a place where the EVMs are have a different implementation of something, like there's an issue. Like now that's a new test case we can add to our corpora that you can test and make sure your EVM is compatible. Kind of the challenges we're running into this is a generalized input. So how can we generate a set of inputs that's standard enough that multiple projects can use these? That's something we really haven't figured out a good way to do. Right now, for our initial run, we're doing state transition tests, so we're operating on bytecode already. If anyone has any ideas of better ways to do this, that would be really nice. One thing that also kills us is speed. So generating the inputs is very quick, but actually the unit under test takes a long time. So if we can generate hundreds every second, but it takes 10 minutes to run a test case, like that's not ideal. So is there, can we break up the super circuit and just test the circuit separately? Like what's the best way to go about this? And additionally, what types of tests should we be doing? So should we always be testing with valid test cases? How do we mutate a valid test case to make it invalid in an interesting enough way to test whether or not the system is operating correctly? Does anyone have any ideas for, at least on the individual circuits, what we should be doing, or maybe better ways to go about generalizing this input?
Maybe Jin is doing a similar testing in the team for about the fuzzing test for MEMC hash. And the idea here is maybe if we can replace the curve with a actually cryptographically non-safe curve, which has a smaller prime number, then maybe we can test it much more faster, and also we can get some inspirations just watching what happens with the smaller prime.
One other thing that we're looking for is how do you know when you have a problem? So in the case of an over-constrained circuit, like what we said earlier, you could maybe fuzz an honest prover, meaning you give it a bunch of valid inputs, and then you don't change it at all, and you have it prove what it should prove. And then if you fail the verifier, you have an over-constraint in your verifier, and that would be like something that could brick a roll-up, right? Or like lock funds in a contract. But then you might also find an over-constraint if you never pass a verifier. But how do we find an under-constraint here, like fuzzing? Like maybe fuzzing isn't the tool we want to find under-constrained circuits, right? Also, we'd like to reason about smaller circuits because like Tyler mentioned, the speed is like, we can't take 700 seconds to fuzz one iteration of the EVM, right? Unless we're like getting something extra out of it, and we'll talk about sanitizers in a second and how we might be able to leverage those in fuzzing. But is it like, can we think of like a common surface on a circuit? Like if we were to take all these sub-circuits out, these like little gadgets, and fuzz them, that we could fuzz the same methodology, right? Honest prover, honest verifier, try to find over constraints, or like, that sort of methodology. And I don't know, is there like, can you guys think of like, if I were to tell you, hey, for Halo 2 specific in this use case, like where would I want to fuzz a Halo 2 circuit, like a small one? And would it be possible to like just pass a -- fuzz flag to my circuit compilation and have it automatically start, which is something that we see like in like memory safe languages like Go are very nice. You can just be like fuzz this and it will automatically like just start for you, right? And the developer doesn't have to write the fuzzer. All right, I'll let that kind of bake for a second. And maybe what we do is there's a follow-up specific to ZK VMs and like attacking subcircuits that we have like a small roundtable about later in another meeting or something. All right, compile time and runtime warnings. There was a really cool tool, I think it was made by Trail of Bits, but I might be mistaken, that would say like basically like, did you mean to constrain this thing in CIRCOM if you assigned it? So like assigned but not constrained, and maybe these aren't like errors, but they're warnings from the compiler. Hey, warning, these cells are unconstrained, like these entire cells. And this would help us find like public inputs that maybe never got assigned to anything later, but also just like were floating. They were completely unconstrained. And you can think of the CIRCOM, the signing, the message signing example that we had. How do we go about like finding those, right? And I don't know what the intermediate representation of like Halo 2 is. I know there's like a TOML file that Leo mentioned in like a Pluff language. These are things that like, for me, like we can have like ideas about how to detect these things, but like what is the crap that we're actually gonna have to write a tool to like look at, and what's the input to that tool? If you guys can think about like all the different like versions of what your circuit looks like from the time that you write it in code to like the time that it's actually being run. It might be that like some intermediate representation there is like the fun area that's the easiest for us to reason about. And if you have ideas for tools for these sorts of things, let us know, please. Another one is like runtime verification. So it's okay to have, we're fine taking a performance hit when we fuzz things for having things that we call sanitizers. So like ASLR moves around and we care about these addresses, but we can also bind like memory regions. And so we basically poison around allocations when we're allocating stuff in regular programming, like in regular fuzzing of like, non-circuit code. And we can say like, hey, did something write to memory that was never allocated? That means we have like an out of bounds, like an indexing array, or there's like a mem copy that's, the length parameter is like, the fuzzer was able to like manipulate that. In this case, we could sanitize the mod multiplication operation. So it's like a shower thought. So I don't know what kind of performance hit that would take, but this would be to look for arithmetic overflows and underflows, right? And so you can think of like, this is more of like, you can't do this with you can't like do this with static analysis and you can't do this at compile time. But what you could do is you could like, everywhere that the mod multiplication operation happens in the underlying circuit, we can instrument that mod and make like a safe mod, right? And so then every time we assign a constraint, we can like basically assign a constraint and say like, I do or I don't care about an overflow here. So custom constraints like these ones here, we could be like, hey, this like last green line on the page, right here, anything on one side of this, like of this equation on the right side, if you modulus this and it wraps around, like throw a warning. Then we can fuzz the circuit and we could see, if we throw a warning, we found an arithmetic overflow constraint. You could also do the same thing for like, I don't know like what a minus would be used in, if that's like even something we can reason about here. And we definitely, like as security people, appreciate like all the like academics meeting us halfway to try to reason about like this gap in knowledge that we have. But yeah, we could also do this for underflows, potentially, right? Cool. Yeah, obviously there's gonna be a performance hit. Yeah, and it would require some tagging by the developers of these things. Let's see, specifying like constraint assumptions. So in the case of the less than circuit, it actually says, like straight up in code, right here, can you see my mouse? Yeah, denotes the byte's representation of the difference between LHS and RHS. Note that the range check of each byte is not checked by this config. This gadget was used one time in the copy circuit, and they did not check that. So like, this is a perfect example of like, hey, we reasoned about this circuit and we made the decision not to include these range checks. It would have prevented this, probably for performance reasons, right? And that makes sense. And whether that was a good decision or not is like, doesn't even matter. The fact here is that we're gonna do this for optimization reasons, and humans are the developers, right? So like, you can't like expect somebody to like, if they're gonna use your, like when you use a library, do you read all the documentation? No, right? Nobody does that. So can we propagate types like with the compiler that would catch this automatically? Is there any type of querying we could do, right? Does anybody have any ideas around that?
I have an idea. So one of the ideas I have is that you could tag every signal as maybe as a range or as a type, and then at some place you add the range constraints, and then the compiler makes sure that when you compose, at least the range constraint is done once. So if you never do it, it will figure out. Because the issue here is that you have a lot of components, you don't want to repeat constraints when you are composing. And here we are reusing a signal, but this also happens when you have lookups. So if you have a lookup to a table, and this table has a range check, you don't need to do the range check again, because if the lookup succeeds, it means that it's range checked. But having like some sort of compiler that can reason out this and tell you, okay, you're connecting this, which is tagged as byte, and this, which is tagged as byte, but I don't see the range constraint for a byte anywhere. You should add it. I don't know if this could be done at Halo 2 level. I think it would be easier to have a higher level language for that.
Yeah, like the Noir language has. The Noir language has these data types. Like they have primitive types such as bool, U8, and U64, which when you declare it in the circuit, you incur these range checks. Yeah.
Awesome. So I think that's a great idea. It's because it helps us like target optimal circuits with respect to like performance. And then you just like, if you're writing in that language, you basically just know like you don't want to add a byte range check, right? Because you know it's going to happen. It also would allow us, we talked just a second ago about like how can we even find unconstrained circuits when fuzzing. You could actually have a compiler flag that's like even if you assume that the user always adds the constraints, you could have a compiler flag that like adds type-specific constraints everywhere, even when it's not optimal. And then you could differentially fuzz the circuit against the non-overconstrained, like extra hardened circuit, which might be interesting. Unfortunately, I think that these are like longer-term projects still. But yeah, one more thing.
There's a way to label columns by region. So one possible thing also, it's in the label of the column for a specific region. So it just try to annotate it, which type or how much bits. At the column level? Yeah, the column has at the region, because maybe in different regions you have different things. So yeah, but the thing is, for instance, like in the EVM circuit, that each column could have a different meaning for each opcode is not very useful. So yeah, at the end you go to the cell level, and it's not enough column. Just a thought, yeah.
Any other ideas? All right, cool. And I think we'll circle back around to this real quick if we have time by like also going back through the bugs real fast, like the different types, and then like, reapplying these filters to them. All right, strong typing, yep, a common language, specifications. Mohammed, do you want to talk about? Okay, symbolic execution and formal verification, and I'm no expert here for sure, and maybe none of us are, but because a lot of these bugs are like obviously like mathematical related and like have like mathematical and like formal properties like ranges, it might be possible to kind of like, well, there's a bunch of different ways. You can like look at the circuits and have auditors try to like break apart smaller sections of the circuit to like formally reason about, which is something that like is a service that I know a few companies are doing. And they found bugs this way, right? So there's definitely something to this. There's also this idea, like I know that Horus, which is the Cairo Lang's like formal verification tool, you can basically inline compiler directives. So like above a variable, like that like shift div 64, you could like specifically say, hey compiler, this should never be anything but 0, 1, 2, 3, or 4. Like you give it a range right there. And that would allow like at compile time us to have some sort of like symbolic execution that like models like smaller chunks of these circuits with their various like formal properties. Yeah, witness uniqueness. ECNI has been really good in these R1CS circuits of CIRCOM. The idea basically is like, hey, can I like mathematically model this circuit, and then can I, for a given like output, does the witness like constrain to a point or a line or a plane, And when you think about it that way, that would be like inputs, like one dimension being an input that's like floating or unconstrained. So like in the case of the message and message squared in that like toy example from the ZKI app class, where we're signing the message but the public input was optimized out by the compiler, this would find that because the like actual inputs would have like the floating message part, right? So the whole space of inputs for a given output would be a line, not a point, right? And that's kind of what we want to avoid here. And in some cases, though, this does have false positives, because sometimes you might want to have a line input, like there's some randomness or something that you're including. I don't know, I can't think of like an example. Challenges, not efficient for generic circuits. It would be insane to like throw a constraint solver at the ZK EVM, for example. Yeah, developer ergonomics. I don't know how, I guess like the way to think about this is like we can make tools to do this after the circuit's been written. We can do this at the source level. We can do this at like some mathematical intermediate representation level, or we can have we can ask the developers to do this with like compiler directives like Horus does directly in the code. There may be like some pros and cons to each of these. Any thoughts or questions, or maybe a good thing to do would be to find these people that do formal verification of these things and ask them, hey, what could you guys benefit from that would either be like a tag from the developer or whatever? Because it might be that like just adding range checks is not that much overhead, especially if we have a strongly typed language. It's automatic. And then that way they could maybe formally verify more of their circuit or something quicker, right? Yeah.
So when you mentioned the symbolic execution, I don't know what to think, but perhaps it's like the mock prover, no? We have been allowed to the mock prover kind of execute the constraints. So perhaps at a higher level we could add more rules that the mock prover can validate, but that that is difficult to put in CKP constraints. And I think of the witness uniqueness, I think Edu is working on something, no? About that, no? Like to help with that.
So I've been experimenting with a tool where you start with a circuit and there's no witness assigned. You try to assign a partial witness, which ideally should be like the input of the circuit, and this tool tries to find other witness values that have unique solutions, but you need to specify a particular input. So I think this is less strict than symbolic execution, which would cover all possible inputs, but it's still useful if you can reason about, like, you try some inputs that try to cover as much as possible, and then you see if there is uniqueness on the output that you think of the circuit.
Can you TLDR what the mock prover that Leo mentioned is?
So the mock prover takes a circuit, a witness assignment, and runs all the constraints and verifies that they are fulfilled with that witness. And the difference with so when you do the real proof, you have the same, but it's very opaque. So when a constraint fails, you don't know which constraint failed. The witness, the mock prover tells you exactly which constraint failed and which values it used.
It's like a debug instrumented version of the verifier.
Yeah, exactly.
Okay. Would it be possible to make a functionality, you can consider it sort of like fuzzing, where you run things through, like let's say you have 5 inputs in a small circuit, and you run it through the prover and you run it through the verifier and you check the output. And then you toggle you like increase one of the inputs or like move one of the inputs. And then you just look and see like, did I get the same output at the prover level? That would tell us that we have like a floating, an unconstrained input. And maybe that's not the best way to find an unconstrained input. Maybe the best way to do it is have a compile time warning that just says, hey, this cell is not constrained at all. But it's another way, specifically through like fuzzing, I guess, that we could find them. I don't know if it makes sense or not. Yeah.
So if you're thinking like fuzzing, I feel like there's like two approaches you can take. Either you like fuzz the ZK EVM by taking like transaction traces like you're doing, right? Or you kind of go into like the circuit level and try to develop more like a generic fuzzer, right? For a specific language, for example, like Halo 2, right? Question is, would it make sense to target the fuzzer at something like the mock prover? Do you think like you can find, for example, under constrained circuits by fuzzing the mock prover instead of like running like the whole proof system on top of it and like the verification as well?
So I think definitely when you want to fuzz, you should use the mock prover, because otherwise you will not learn anything. You just know that. So first it will take
Right.
more time to generate the proof, and once it fails, you just know that it failed, but you don't know how it fails. And the point, so I imagine you could take a valid witness, pass it, and then run it. But I don't know how you would reason about the result, because it could be an under constraint. It could be that you generated a witness that is supposed to be invalid, so it fails. So it could be a correctness issue or not. And even our circuits have lots of free witness values, so they are not constrained in certain situations, but that's by design. And you don't have the metadata to know that, so when you hit that, you don't know if it's okay or not. Also, even we don't have, so at the circuit level that you would fuzz, you don't know which witnesses are inputs, which are outputs, which are intermediate.
Right.
So I think we're
I see.
lacking a lot of information to be able to do some smart
Yeah.
fuzzing.
I see. Makes sense. Cool. Thanks.
Another thing I think in this vein that we miss
Another thing that I think we are missing CKVM in this vein is kind of like in our automatic tests, we don't have like the what we call the evil prover test, like we that CC called it evil prover. But the thing is like we are using like we are getting an input a block, and then we are using our own witness generation to generate the actual witness in all the tests. So we don't have tests yet that actually are based on witnesses that doesn't run our witness generation. No, like another prover could generate like like a different witness. So I'm missing that. Yeah.
There was a specific Aztec bug where there was no constraint. Like if you're appending to a Merkle tree, you have, like if the tree looks like this, right? And you want to add something to it, there's like some kind of spec that's like, hey, like the first leftmost leaf, like this is where you should put it. There was actually no constraint that you didn't stick it over here. And the actual like index in the tree was a private input. So had their prover been malicious, they could have made a tree that looked like this. And if nobody knew, and it could be that there's like tons and tons of places to put a leaf, right? If nobody knew what it was, then nobody could have pinned to that tree. So no other prover could have done it. So like they would have been the only prover in the world that could have like progressed the state of this forward. And that would be an example, I think, of like what Leo mentioned of like, you need an evil prover here. If you're testing your verifier, you need an evil prover, right? If that makes sense.
That's for under constrainment, no? For test.
Yes, yeah. The way that I reason about it is like there's constraints at the proving level and at the verification level. And in order, like you could fuzz all day through an honest prover and never find an under constraint in the verifier. And I don't even know how to reason about fuzzing just the verifier. Because then you end up in this case where you have false positives left and right where it should be failing. So
No, it's like I think you should fuzz it after the witness generation. No? I think
yeah,
that's better.
for the mic,
The witness generation that you have implemented first.
Leo said for the microphone, you should fuzz it after the witness generation. I think the problem here is that like, let's say you fail. How do you know that like it shouldn't have failed? You see what I mean? Like, is it a false positive or not? So like, it's very interesting. I guess what you could do is after the witness generation, well, I don't know. I actually don't know how you could go about doing this.
Also, if you think about fuzzing the witness to find under constraints, there is a challenge, which is you need to reason a lot about the constraints to have some interesting fuzzing results. So imagine you have a circuit that inside the witness has a counter that goes from 0 to 10. And maybe you think it always starts at 0, but there is no such constraint. So you start with a valid assignment, which is from 0 to 10, and that works. Maybe a witness that is not supposed to work but works is from 1 to 11. But if, to hit that like 1, 2, 3 to 11 with fuzzing is really hard to get, because I mean, maybe you only have the constraint that each value is +1 from the one before. So yeah, so you skip the fuzzing, and yeah.
I think like using fuzzing can help to maybe find the error, but some error that not actually come from the paper. Like the people who write the paper, they completely right on it, but the implementation is wrong. So, what do you think with this kind of bug? How we can detect that? Just like a long time before, the library, like the OpenSSL, they have problem with the algorithm and the people who decide the algorithm.
So I think, like, to summarize the question, if there's a specification for the proving system or whatever have you, that the implementation is correct. This is actually something that like Tyler and I work on all the time, and that's, we have a specification for how like honest validators in the beacon chain should work and what the data types like serialization, unserialization should look like. And then we have 5 different client teams that implement them in different languages that actually are the software developers that write it, right? From this like specification that we have pseudocode for, but then like, you know, is really just written down in English to like the implementation. There's 2 ways that I think have been like really, 2 things that have been really fruitful in finding where people misalign with the spec. One of them is like understanding the spec, having a pseudocode for the spec, and like in the Ethereum specification, it's actually written in Python, and then like manually reviewing it. The other one is differential fuzzing if there's multiple implementations, right? But actually maybe there's a third here, and that's that if you have a specification and you have pseudocode for the specification, then you can generate tests for the specification. And then anyone, if they come implement something in different languages, can like ingest your test if they build bindings for their language. I don't know if that will help a lot here, but I do know that there may be something to doing like differential fuzzing of these ZK EVMs. The problem with differential fuzzing, like differential fuzzing in the process, like let's think about an EVM. If we want to differentially fuzz Go Ethereum versus like Besu versus Aragon and Nethermind, which are all different, you know, versions of the EVM, we can provide them a pre-state. We can have them process a block or process a transaction or whatever have you, and then we can diff their post states. But in the case of these ZK EVMs, there's no like state. It's just like, this is all just like generating a proof that the states were valid. Like, so you're starting with valid states and post states, right? Or invalid. And so it's kind of hard to reason about that. Yeah, but there may be like assertion statements that you could write into circuits like ahead of time to be like kind of like the way I think about it, like if we're instrumenting the mod functionality to fuzz and look for overflows, that idea, like kind of like that you would be like, that the developer could write and be like, this should never be negative, right? Shift should never be larger than 4, like things like that. I don't know what that would look like though, right? And maybe that's more for like the proving system authors than it is for like the circuit developers, but which we have some of both in this room. Any other ideas, comments, questions? Okay, I think the last category here is just education and best practices. I mentioned the bug tracker. If you just search ZK bug tracker on Google, it will bring you to the 0xPark one that Kyle made, and huge thank you to Kyle for that. You file an issue there. If you tag somebody from that repo, you tag Kyle. If you tag, I'm in InfoSec, like information security, InfoSec UAL on GitHub and Twitter, whatever. If you tag me, I'll triage it too if you don't like want to spend all the time writing up the bug. I like reasoning about these things, and this is like my job, so just feel free to kick it to me, and then that way I can classify it and get it in here, and then we can like discuss about this in a year when we have 10 more new types of bugs that we've all introduced. Cool. Yeah, so I want to do this one last like run back through here. So given all the different like fuzzing, formal verification, compile and runtime warnings, these types of things, and then going back and looking at these bugs, like let's think about them that way. This general missing constraint, I think is the hardest one. It's always application specific. It's like a logic bug. It's nothing new in security. It'd be really hard to apply methodology for discovery here, right? Anybody have a disagreement? Okay, so I'm gonna skip this one. Arithmetic underflow, overflow. Mention the like instrumenting mod, any type of like minus type operations in circuits. Does anyone else have anything else here? Maybe formal verification. Maybe if we like can tag a constraint as being like this should never overflow or something, and then have it reason about it in like static analysis. Halo 2 people, what is the intermediate representation of your circuit before it's all circuit? Can you hand me like a big spreadsheet, like a CSV of equations? Like,
So I built a tool that gives you that. Awesome. So I can send it to you, some results.
okay. I think it would be good to especially get Mohammed looking at that, see what maybe we can extract from that. And it may be possible then to tag columns the way that Ingtong's like dynamic advice lookup table fix suggested, or tag individual constraints. And then if we could map them to this like table of equations, that would be actually maybe something we could do in the next 2.5 weeks to finish before the residency. Any other ideas? All right, cool. Types and links. A new strongly typed language. Definitely like a reach goal. I think long term, absolutely reasonable, right? Short term, does anyone have any, or long term, any other ways to kind of reason about this? I think maybe education's really the only other, like explaining to everybody. I think there's like a point in every developer's like path where they realize like, what is the computer actually storing my variable as? Like as an integer, and what does it look like? Flip that on its head, because now it's in a prime field. So like maybe just making people aware of like the natural range checks that have to happen here, and what happens when something's signed or unsigned.
Yeah, I was gonna say.
Here, let me run this mic back.
I didn't know like Nuad had type checking, but I think it like is good because the more abstraction you do, the better it is to like type check. Because I guess when you write like higher level languages, you won't realize there's overflows in like prime fields. Like if you write in Halo 2, it's obvious, but like if stuff like Nuad, you probably want like those type check things. And maybe in the type system, you can include something about overflows. I don't know. But yeah, I think that is probably the way to go regarding like type checking. Like just build it into the language like Nuad does. I don't know how Nuad does, but like that seems good.
Yeah, that's really good advice. I also think you could, let me find this example. Intermediate variables are a way that what you could do this. So like in this particular, where is it? Too many examples. So you could imagine a case where this gets you just under P, and then this pushes you over P, just this addition. So having an intermediate variable, a separate assignment and constraint that checks that, and then one that checks that is better. Like, what if I multiply 15 numbers together? Like, that's way more likely to have an overflow that reaches P. But if I like had like a step where each time I multiplied and added, then I could do a range check on each one at the like static analysis or like the symbolic level. So this is like another, maybe we get enough examples of this that when we realize that it doesn't happen when you never have more than like 2 to 3 variables in a constraint. That's like more of like an education, like a circuit developer education thing, like in a best practices. Any others? Oh yeah, we were on the types, links, nothing else there. Assigned but not constrained. I think there was one idea of like compiler warnings, like telling you that this is like this cell is not constrained in any way. Anything else that you guys can think of? Non-deterministic circuits. This is no different than mod P and a few other like corner cases in my mind. Does anybody have anything here? Unused public inputs, very similar to the assigned but unconstrained. We mentioned like fuzzing where you move them on purpose, but then Edward did mention, a lot of times public inputs in general don't matter, and maybe I'm just, this is a weird example. I'm imagining an opcode that takes one argument versus 2. The second one can float and it's fine, and that's valid functionality because it doesn't go anywhere. Yeah, anything else? Anyone else? I think we have a good fix on the way from Ingtong for this one, where we tag a column. I think this column tagging idea might permeate into other areas, like when we want to say that all of these constraints should not overflow versus ones that we're okay overflowing. Anything here? This is like, this is maybe like a bug that we tripped over one time and hopefully doesn't come back to bite us in another future proving system, but maybe circuit developers don't care about. All right, cool. I think that's it. Any questions, random ideas, inspiration? All right, awesome. Thank you, everyone. I think we're basically at lunchtime. All right, cool. Come find us if you have other ideas. You don't want to say them.